Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Ishaan Kannan from Harvard, who will tell us about foundations for quantum speedups in noisy quantum experiments. So Ishaan is a first-year graduate student in the Harvard Quantum Initiative. His advisor is Professor Jordan Kotler, and his interests is in various applications of quantum information processing to chemistry, high-energy physics, and astronomy. In particular, his work is centered on our understanding of how abstract theoretical insights from quantum sensing and learning theory can be realized as practically meaningful gains in future quantum-enhanced experiments. And this includes the design of these quantum-enhanced experiments that retain quantum advantage even in the presence of noise. So proposing quantum sensing strategies, leveraging near-term quantum devices, and developing learning algorithms for characterizing molecular systems with quantum probes. So Ishaan, the floor is yours.
Great. Yeah, thanks so much for having me. I'm very excited to tell you about recent work that I've been conducting over the past year at Harvard. So let's get started. So I want to start by recounting the emergence of the field of quantum learning theory in recent years, and to sort of understand what its core message is. So a core goal of quantum information science is, of course, to find useful applications of quantum computers. However, we live in an age before we have fully fault-tolerant devices, and so in lieu of tinkering with an actual device, we want rigorous proofs of quantum advantage. Now, historically, the known examples have resided in the computational realm, and that's most notably in, for example, cryptography and quantum simulation. However, quantum learning theory came about and asked a different question. Suppose I had a quantum computer in my lab. What could I do with it? So the high-level picture you could have in mind is, you might imagine a wide array of physical experiments ranging across, for example, astronomy, material science, or chemistry, in which quantum data is collected from the process of actually doing the experiment. And unlike in the classical world, where that quantum data must first be measured and converted into classical data before you can, do inference on it, you can imagine actually coupling a quantum processor to the experiment itself, and then asking what features of nature can be learned by doing so. Quantum learning theory then came in and asked whether there could be a quantum advantage in actually learning from the natural world, and moreover, whether there exist laws of nature which we could only hope to discover if we had access to quantum information processing. And how could we even rigorously prove such an epistemological statement? So the core thesis that has since then been adopted in quantum learning theory is that indeed quantum information processing can enable experimental discoveries that are otherwise impossible. More concretely, however, what the statement really says is that there exist certain quantum objects, such as states or dynamics, for which a classical experimenter, if they wanted to learn some property of that quantum object, would require a lifetime of experiments. But a quantum enhanced one could learn very quickly. But this sounds a bit too good to be true, so let me sketch the landscape behind this core thesis a little bit more for you. So when the field came about, the early results in quantum learning theory were really of the kind of, scientists speculating about what a future in which we had fully fault-tolerant quantum computers could look like. And so they weren't setting out to establish here is a concrete experiment which in the future will be exponentially better. They were instead stating mathematical existence results, that there are some mathematically valid states and unitaries that I could write down such that you need a quantum computer to learn about them. That's not to say that those particular examples are immediately relevant to any particular experiment. However, over the last several years, as the field has developed, the majority of work has actually been on adding to this treasure trove of contrived but exponential quantum advantages. And work has not been so much on actually building a road to realize those advantages in a useful experiment. But today, we'll see that building that road is actually not a question that quantum learning theory, as it was developed previously, is particularly equipped to solve. This is a perilous road that will require a new approach. So in this talk, we'll start by understanding why it's so hard to build that road. And what we'll see is that noise will degrade the very primitives upon which quantum learning advantage thrives, even if you had a fully fault-tolerant quantum computer. Then we'll ask what the actual road looks like. And that'll involve 2 points. First, quantum speedups that are actually aware of the noise at the interface between your quantum computer and nature. And moreover, making that interface itself robust. And then we'll talk about an important example, which is uploading quantum states into fault-tolerant memory. So to start, I want to understand a model for noisy fault-tolerant quantum learning. So first, it will be important to understand how quantum learning theory actually formalizes the resource cost of physical experiments with and without quantum information processing. So the starting point of quantum learning theory is to reframe quantum experiments as processes of learning from nature by performing inference on collected data. So what you might imagine as a very high-level schematic is there's some quantum probe that interacts with nature and collects some data, and is then coupled into a quantum processor for processing. Now, the learning theoretic formalism takes this picture and treats the physical experiment as an oracle which generates quantum data. So this is like a black box, which contains the unknown details of some physical system at hand. And a scientist can query the oracle despite not quite knowing how it works. Now, oracles are extremely common in theoretical computer science. And so this reformulation is actually what gives us a mathematical footing to begin a rigorous search for quantum advantage. So in quantum learning theory, experimental trials correspond to oracle queries, and many examples of potential quantum enhanced experiments have actually arisen from this interpretation. So upon querying an oracle, which is like some physical experiment, the learner obtains copies of some quantum state, or the ability to access some quantum dynamics. And so once this is done, quantum learning theory then allows the learner to manipulate this uncharacterized quantum systems as they wish to learn about it. Now, while a quantum enhanced learner can directly apply quantum information processing to the post-oracle quantum state itself, the classical learner must first make destructive measurements and then perform classical post-processing on the data. So this is the precise setting in which quantum learners can obtain an advantage. And so as such, we can reformulate the mathematical hardness of learning about a quantum system via the language of query complexity, which is how many times a quantum versus a classical learner needs to run an experiment to learn about the physical system at hand. Then the statement of quantum advantage is usually that the number of classical queries, regardless of how clever a classical algorithm you use, is provably exponentially larger than the number of queries needed by a learner that has access to a quantum computer. And so it's in this way that we try to answer the original fundamental question by saying that if we were only limited to classical post-processing, there are certain aspects of nature which we could never discover given, say, the age of the universe, since the number of experiments we'd need to run is enormous. So this all sounds very nice. However, in practice, many of the actual examples that obtain a rigorous advantage use the same set of primitives under the hood. So many of the advantages that we know of in quantum learning theory are secretly kind of the same thing, under the hood. And the primitives that really enable these, by and large, are Bell sampling, swap tests, and more generally interleaved control, in which you interleave quantum control with queries to the oracle. And so I'll touch on what these are a little bit more specifically later. Now, the statement of quantum advantage, as I said, is if you do not have the ability to perform entangled processing, then you require exponentially many samples, whereas if you can run one of these primitives, which uses entanglement, you only need a few samples. However, crucially, it is assumed that everything we do is noiseless, because we hope that one day we can use a fully fault-tolerant quantum computer. But now I want to focus on that last assumption and ask if it's really realistic. So here on the left, I've drawn a setup you might envision in quantum learning theory. So there's some quantum sensor or probe, which is exposed to nature, and then it's coupled to a quantum computer. And we can describe this a little bit more, slightly more rigorously with a circuit that looks like the following, where, queries to this oracle appear as loading some quantum data onto your quantum circuit. And then you can interleave that quantum data with processing in the form of unitaries, state preparation, measurements, essentially whatever you wish. However, on the right, I'm going to redraw essentially what's actually happening when we try to run this experiment. This is going to be in a less idealized way, where we include the noise that's secretly happening under the hood in the left picture, but we try to sweep it away using error correction. So a circuit description of what's really happening looks as follows, and a clear asymmetry will arise. So while you might have the ability to actually perform quantum error correction on our processor, the system we're trying to learn about is coming from nature. And a priori, it need not be compatible with quantum error correction. So as such, errors that actually happen, during interactions with the physical system itself might be substantially more difficult to handle than ones within the processor itself. And so my key assertion is that even if you had future fault-tolerant devices, you couldn't actually treat everything as if it were noiseless. But now this raises an important question. Is it the case that this more fine-grained picture is simply a technicality, and indeed we can actually do what quantum learning theory claims to do, or does it actually change how we need to think about the idealized model of quantum learning? To study this motivates us to instantiate a theory of noisy quantum learning. As I said, in noisy quantum learning theory, quantum error correction can take place on logical qubit registers, but interactions with nature can be unprotected. And to formalize this, we introduce a computational complexity model for noisy quantum learning. This is called NBQP with an oracle O, where the oracle represents the system in nature. And by studying this model, our goal will be to ascertain whether the most powerful class of quantum-enhanced experiments we can envision in the future actually matches the vision that has been studied in quantum learning theory, or whether we need to change our mindset. So how do we model NBQP in a truly encompassing way? The rigorous definition is as follows. So we allow circuits of the following form, where each V might be a depth 1 unitary on some polynomial-sized register of qubits, or a query to an oracle O, which acts on n qubits. And importantly, in between each layer of quantum processing, we apply local noise to every qubit IID with some constant noise rate. Then at the end, we're allowed to measure in the computational basis. Now note that this model actually permits things like mid-circuit measurement and qubit initialization. So without baking it in explicitly, this model already has all the ingredients we need for quantum error correction. And one note is that if you take the limit where the noise rate lambda is 0, you exactly recover the definition of BQP, which is the model for noiseless quantum computation that you might be familiar with. And so that's exactly what you want in such a definition. And so for those who are familiar with previous work, which studied the computational complexity of NISQ devices, this is quite different. This is literally a model for a fully fault-tolerant quantum computer. And without an oracle, NBQP is exactly equal to BQP because of the existence of fault tolerance. Now, the non-trivial question opens up when we introduce an oracle, which is really asking whether for learning problems, does NBQP functionally equal BQP? So we've introduced NBQP with an oracle as the class of learning problems that can be solved with a real quantum computer. The most sophisticated quantum-enhanced experiments are only as powerful as NBQP. And so we need to do this replacement in our minds. Instead of studying BQP with an oracle like quantum learning theory really does under the hood, we make this replacement. And the question is, how powerful really is this new class?
Sorry, can I just ask a question about the definition?
Sure.
Just wondering. Just wondering.
Go ahead. Sorry, I can't see you, but I can hear you.
Oh, that's fine. That's fine. So like, I guess, sorry, I couldn't exactly follow the definition you said, but it seemed like you had a constant depth kind of circuit in between the sensor's output and getting the quantum information into the quantum computers QRAM or whatever.
So
you want. There was some kind of constant depth circuit in between. Is that right?
Well, so okay, the process of loading the data onto the quantum computer itself is black boxed as quantum depth, as constant depth.
Yes.
Yeah.
Okay, so you're talking about a depth one unitary here, and I wasn't sure what V is. So
sorry.
You talk about a depth one unitary V.
Yes.
What is V?
So the point is that each layer of any quantum circuit is modeled as a depth one unitary. So if you have 2 qubit gate, it's a unitary composed of 2 qubit gates such that no qubit is acted upon twice. And so the point is, in parallel, it is the each V you see here, these V sub k's are just depth one quantum circuits. And the point is that at every level, every layer of your circuit, you will incur noise. So this is the model commonly used when you study fault tolerance. You assume every time step incurs constant noise.
Yeah, but I'm just trying to understand where this unitary is acting. I mean, you're trying to generalize to a more physical setting where the quantum information that comes in from the environment, from the sensor, it can kind of experience noise on its way into the quantum computer, into the logical qubits, right? On the quantum computer. And so I'm just trying to understand what your noise model is here and where this depth one unitary comes in.
Yeah, so the point is each V here in your circuit can either be a depth one unitary of your choice, so you can perform whatever gates you want, or it can be a query to the oracle, to the quantum data that's coming in from the sensor. And every V, whether it's a query to the oracle or some quantum control that you choose to apply, is surrounded by constant strength local depolarizing noise.
I see. So can I just ask, so in this, I mean, one could potentially take this one step further, and I just want to know if that's already included in your model or separate. So one could kind of say, well, actually, when you're doing a quantum query into the environment, because you're now in non-fault tolerant land and all sorts of noise can happen, you're actually very restricted in the kinds of queries and the kinds of quantum states you can observe. And so you could imagine, putting this, you have some log depth restriction on the quantum kind of circuits that will extract quantum information from the system. So does your model kind of put that restriction on, or is that a separate restriction that goes on the oracle itself? That's
exactly. So that you could study that setting, but that would be a restriction you specifically put on the oracle, and that can be studied within this model, indeed.
Right. Thank you.
Yes. Sure. Any other questions? I can't see people, so just feel free to speak up. Okay. Right. So, great. So yes, right. So we've introduced NBQP, and now first I want to touch on some complexity-theoretic implications of this definition. So while we know that NBQP equals BQP without an oracle, we will see that adding an oracle actually changes the game substantially. And the first major result to that extent is that NBQP, there exists an oracle O relative to which NBQP is exponentially separated from BQP. And the interpretation of this is that natural quantum learners may actually be exponentially weaker than their idealized counterparts. So there exist cases in which the idealized model of quantum learning theory really is not valid. And shortly, I'll explain a more practical version of this abstract statement. But this also raises a natural question, which is, if NBQP can actually be so much exponentially weaker than BQP, is it really the case that fault-tolerant devices are any better for learning than the NISQ ones that we already have today or in the near future? And the answer to that is also in the affirmative. And so here we use a computational complexity model of NISQ, which was introduced in this previous work, which is essentially interleaved circuit noise, but you cannot do mid-circuit measurement or state preparation. So you remove the specific ingredients you need to perform quantum error correction. And so once again, now the interpretation is that there exist learning problems for which the ability to perform coherent quantum depth is truly essential. And so we're left with this kind of hierarchy relative to oracles. Now, now I want to turn to talking about some actual quantum primitives you might imagine using in a quantum enhanced experiment and take a step away from this more abstract picture. So first, let me just touch on the two canonical learning primitives I mentioned earlier. The first is the swap test. So the swap test is essentially the circuit that you see here, and it lets you measure the inner product between two quantum states. And more generally, general versions of the swap test allow you to measure nonlinear observables, such as the purity of a quantum state, using constant depth quantum circuits and a constant number of copies of the state itself. A second primitive that's ubiquitous is Bell sampling. So Bell sampling says, suppose I want to know the expectation value of a large number of Pauli observables of some quantum state. Now, Pauli observables, of course, form a complete basis, so this is very useful information generally about a physical quantum system. And so it's known that by using Bell sampling with only linear number of copies of a quantum state, you can estimate an exponential number of Pauli expectation values. So these are two primitives that actually power most of these quantum learning advantages. Now the question is how that fits into this NBQP framework we've just introduced. So first I want to talk about noise and the swap test. So the canonical result, this is the very well-known separation in the field of quantum learning theory, is that if you want to decide whether an n-qubit state is pure or maximally mixed, in the worst case, if you do not have access to entangled measurements across multiple copies of the same state, you will require exponential and n number of samples to do so, whereas only a constant number suffice via the swap test to do so if you can just make these joint measurements across multiple copies. Our result is that any NBQP type strategy, so now you have noise at this interface between the processor and the state, but you could perform error correction if you wanted. Any NBQP strategy making joint measurements on two copies of a state row requires an exponential in the noise rate number of measurements to distinguish between pure and maximally mixed. So the point is, as the noise rate increases, the number of copies we need exponentially grows, and there's no way to circumvent this. So the consequence is really that the swap test itself is not noise robust. Secondly, Bell sampling. So the canonical result, once again, is you only need linear samples to learn exponentially many Pauli observables. But even if I gave you k ancilla qubits of memory, so now you're allowed to retain a coherent memory of k qubits throughout all of your experiments, you still need exponential in the difference between n minus k samples to learn all these Pauli expectation values. The result we showed is that this precise lower bound is what holds, but with a damping factor that's exponential in the noise rate once again. So namely, if I took k equal to n, that would imply I actually have the ability to do Bell sampling. So I could do the algorithm that noiselessly takes only linear samples. And now I will require exponential in the noise rate samples once again. And Bell sampling itself, if you just compute the actual sample complexity, scales like this 1 minus lambda to the minus n factor, but with a different constant. So it's essentially saying that Bell sampling itself gets exponentially degraded. Once again, estimating observables is exponentially costly in the noise rate in a way that no form of quantum error correction could ever circumvent. So this is kind of an unfortunate story, right? Like the very primitives that enable quantum learning advantages are so fragile under noise. And moreover, it actually is the case that the very classes of states that enable those learning advantages are themselves fragile under noise, because the features that made them hard to learn without entanglement are actually, highly non-local. So how can we hope to actually perform quantum enhanced experiments in practice in a useful way? And so that's what I want to touch on next. The first point I want to make is a very simple one, but it's one that's conceptually important. So if I just put that same theorem that I just showed up on the board, there's an immediate corollary, which is that suppose I let n sub single copy be the optimal cost of any single copy protocol, and I let n sub 2 copy be the sample complexity of Bell sampling, but now in this noisy setting. The ratio between these two, depending on the noise rate, can still scale exponentially. So the point is that at finite size, there can be some gains that actually do look like they scale exponentially and can help you in a meaningful way. But let me just explain the same thing pictorially to make it a little bit clearer. So, we have two models of doing Pauli shadow tomography, learning a bunch of Pauli expectation values. In one model, we can only process a single copy of the state at a time, and the other, we can do Bell sampling on 2 copies. And then, we infer these expectation values, and there's the ratio in between these 2 sample complexities is plotted as exponential of n times some factor that depends on the noise rate. And the point is that as long as you're a constant gap away from some fixed noise rate, you can actually compute this noise rate. It's something like 0.2, so it's quite large. As long as you're a constant gap away, you actually will have an advantage that looks like it scales exponentially. And that's quite useful in practice, even if the asymptotic result is not as pretty. The core message is just that quantum advantage can persist in a noise-dependent form that scales exponentially at finite size. The next point I want to make is not yet a mathematically rigorous one, but it is nonetheless a conceptual point that I think is an important open direction for both quantum learning and physics itself. So the high-level point is really that physical systems often have native error-correcting properties. So examples include tensor networks, such as versions of meras or models inspired by holography. These actually have intrinsic error correction properties that arise from their kind of hierarchical structure. And what inspired a lot of this was actually the broader concept of the renormalization group. The act of performing a coarse graining to extract macroscopic, non-local information while washing out fluctuations at a local level is very, very reminiscent of error correction. And it's actually what gives these renormalization groups based error correction codes their performance. Moreover, the fact that local subsystems of a chaotic quantum system look indistinguishable from a Gibbs state, while the larger system retains memory of the initial conditions, this is the hallmark of quantum thermalization, and it's also extremely reminiscent of quantum error correction. So an interesting question is whether this qualitative point can actually be leveraged quantitatively in experiments. One idea is some kind of passive error correction, where we can attribute the fact that our measurements can efficiently extract the desired information to some kind of error robustness going on under the hood that's related to, for example, the renormalization group. Another is a form of active error correction, where we utilize known properties of the physics to actually decode the outcomes of noisy measurements in post-processing. And so to be just a little bit more precise, we know that in fields like holography and thermalization, people have developed quantum error correction codes motivated by these rich underlying physics. The question is whether we can actually take a step back and talk about the noise robustness of the physical system itself, rather than a toy model for it. Okay. So to recap this first part of the talk, the second part will be a bit shorter, but to recap it, the first result we saw was that this model for noisy quantum learning, NBQP, is strictly contained between NISQ and BQP. So while future fault-tolerant quantum computers are indeed stronger experimental tools than NISQ and classical devices, the idealized BQP story that we've been working with for years in quantum learning theory is lacking. The most powerful tools we have are degraded by noise in a way that no form of quantum error correction can recover, but hope is not lost. We have outs in physical noise robustness, or in contending with finite size gains and being more deliberate about the kinds of advantages that we seek. So I want to actually pause here if anyone has any questions, because the second half will take a lot of this, but also talk about something a bit different. Okay, great. I will move on to the second half, which is about noise-aware quantum speedups. So we've seen thus far that noise poses a serious obstruction to the kinds of quantum advantages that quantum learning theory has developed thus far. To begin this section, I therefore want to talk about how we can actually build a robust interface between a quantum processor and quantum data from physical experiments, and start to recover some of the gains that are actually promised by quantum learning theory. So let's start with a reinterpretation of the results we've just discussed. We've taken quantum and quantum learning advantage to mean obtaining a speedup in inferring features of a quantum system in nature by processing data coherently. But the fact that noise degrades our inference can be interpreted as a data interface bottleneck. That is, data that exists out in nature is not equivalent to data that we have in a protected quantum memory, because we can't just go and apply sophisticated quantum processing at the unprotected physical qubit level if we're working with fragile quantum systems. And, of course, the most interesting systems we might hope to process are also, the ones that are also the ones that generate the largest advantage. These are the ones that are most fragile under noise. These are highly entangled states that have extremely non-local behavior. And so the more we manipulate them, the more we destroy that interesting non-local behavior. And also, we just only talked about primitives such as swap tests and Bell sampling, which are actually depth 1 quantum circuits. We might actually want to perform even stronger primitives that use deeper quantum circuits, where we apply many layers of quantum operations to unprotected physical states. This includes, for example, classical shadows, quantum principal component analysis, quantum signal processing. These are primitives you might have heard of, which are extremely useful have been extremely useful in quantum computation in recent years. But so far, it seems like these will be very hard to use in practice. So once again, the big challenge is that quantum data that we find in nature is not equivalent to quantum data stored in an error-corrected memory. What we might hope to do is first find some way to take the states that we obtain from nature and then store them in an encoded memory. Now, in the classical world, this is very easy. If we get classical data, we can just copy it as many times as we want. But the no-cloning theorem prevents this from being possible in the quantum world. So when we're given an arbitrary unknown quantum system, we aren't actually just a priori able to move it into an error-correcting code of our choice. But if there did exist a procedure to do this, it would have the following requirements. First, it should be scalable. And by that, I concretely mean that the error overhead we incur in actually moving the state into a quantum memory should be small and also independent of the final distance of the code. Now, the reason we want this is because, as quantum systems, we want to preserve a quantum advantage that scales in system size, which will then require us to, potentially apply deeper quantum control. So with larger systems, we'll need deeper circuits, and we want this procedure to work independent of how deep of a circuit we want to run. Second, we need flexibility, which concretely means that it should work for any input state without us having to know anything about that input state. Third, it should be practical. We want an efficient circuit that we can just directly run to do this kind of uploading into a quantum error correcting code. And fourth, we need logical fidelity. Once the state is in the error correcting code, any residual errors that persist at that point in time should not then propagate to cause logical errors regardless of what circuit we choose to run after the fact. So these are some strong requirements that we actually need if such a procedure did exist. So to reframe this pictorially very quickly, this is really what we want. We imagine some physical experiments, and we have some procedure, as you were alluding to earlier, where we try to transduce it into a quantum processor, and that transduction procedure is experiment dependent. For example, in optics, we might be able to implement certain qubit photon gates. That's like one example. But then we have a question mark where we need to be able to interface that data with a fault-tolerant circuit. And the question mark is, how do we actually do this? To accomplish this, we look to a concept from fault-tolerant quantum computation, which is magic state injection. In the context of fault-tolerant quantum computing, injection is just a way to enable non-Clifford gates. So the problem is we're able to find ways to generate single qubit magic states, but we need them to be compatible with a quantum error correcting architecture if we're going to do, universal computation. And so to achieve this, we need to lift that single qubit magic state into a logical qubit magic state. A clean way to see this is actually through the example of a surface code state injection. So this is now well understood that if you prepare a single qubit magic state and you prepare a bunch of ancillas in the right geometry and in the right initial product state, and then you just start to measure the stabilizers of the surface code and just grow along the patch. If you do this a number of times, if you measure these stabilizers a number of times, that scales with the distance of the actual code you're trying to inject into, with quite high fidelity, you actually end up with the logical magic state you wanted on the surface code patch. Now, while this has been a concept of much importance in practical quantum error correction, it certainly seems like it could be useful to interface, fault-tolerant quantum circuits with quantum learning experiments, if we could actually inject arbitrary states rather than just magic states. Now, the procedure I just described to you satisfies scalability. So it turns out that the eventual error rate of doing this, at least numerically, turns out to be independent of the eventual distance. And it's also practical because, of course, this is just a concrete surface code, stabilizer measurement circuit. However, as I've stated it so far, it doesn't yet satisfy flexibility because it's not like I'm telling you I'm using a magic state. I'm not yet telling you I could put in an arbitrary state. And because of that, it also doesn't necessarily satisfy logical fidelity. It could be the case that if I put an arbitrary state there and injected it, there might exist some residual errors which would cause faults in some computation. However, by using the results of this recent work, which developed a composable framework for fault tolerance, it actually becomes possible to establish those last two criteria. Oops. Okay. And sorry, there we go. Okay, so now that we have the idea for what this quantum uploading procedure is trying to do, I'll tell you what the conclusion is and then what the consequences for learning really are. So the upshot is that the true traits that were missing before can actually be established. And so what we did was we actually proved that this flexibility and logical fidelity can be obtained in the optimal depth. So in a circuit of depth that's linear in the distance of the eventual code, we can actually obtain this kind of quantum uploading gadget. And so, this fills in the picture, the question mark we had before with injection and growth, which allows us to couple a physical experiment to a fault-tolerant circuit. And now, the important consequence is that any noisy experiment can be turned into a noiseless experiment with one layer of noise at the outset. So the point is that any errors in the experiment, the transduction, and the injection step all actually happen before the actual processing, before the circuit that you run. And so theoretically, you can treat them as a single noise channel that happens at the outset of your learning algorithm. So before we talk about using this for specific tasks, I actually want to pause on one important consequence of this observation. Before, we stated the conclusion that NBQP with an oracle is strictly contained within BQP. It's exponentially separated. But because of the existence of injection, we actually see that the picture is much, we have a much clearer picture of the relationship between these two complexity classes, which is that NBQP with an oracle is actually exactly equal to BQP with an oracle that's been acted upon by one layer of noise. So any subsequent, it turns out that no matter what problem I cook up, any amount of error in the actual NBQP type circuit can always be just moved onto the oracle itself. But having seen this more complete complexity theoretic picture, we can also talk about some concrete utility here. So now I'll describe some common learning tasks where our previous results might have suggested that noise should erase these advantages. And I'll show that by using uploading, we can actually obtain exponential time and resource savings in the presence of noise. So in the following, let n sub raw correspond to the most optimal adaptive strategy that does not use quantum uploading. It can use a fault-tolerant processor, but the strategy cannot make the choice to immediately upload or encode the state that you obtain from the experiment into an error-correcting code in the way that I just described. Then the consequences as follows. So suppose I want to estimate k-local Pauli operators. So this is a very common application of classical shadows that people have talked about for years. It turns out that the ratio between sample complexity of a raw versus uploaded protocol scales exponentially in k. And this ratio is actually information theoretic. The point is that no matter what raw procedure you use, it will require exponentially more samples than a procedure that does uploading and then classical shadows. And so this is really a way to actually recover the classical shadows algorithm in the presence of noise. Second, suppose we want to estimate nonlinear properties of quantum states, like some observable of rho cubed. Once again, the ratio between these two sample complexities, information theoretically, will scale exponentially in the size of the quantum states. And actually, the reason these are two important examples is not just because of these specific examples, but the principles they embody. Because a majority of algorithms that have provable learning speedups, as I said, they do the same thing under the hood. They actually rely on two broad classes of primitives. Randomized preprocessing, of which classical shadows is by far the exemplar of that class, and multi-replica measurements, for which swap tests and generalized swap tests, like what enables this kind of measurement, are also the exemplar of that family of protocols. So in short, these two examples should give us the intuition that uploading is actually indispensable for implementing a broad class of learning primitives in practice. But now to ground this a little bit in a more practical experimental proposal, we can consider benchmarking the utility of uploading in the following setting. So what we consider is actually an astrophysical imaging task, which is studied in this work stated here. And this task is simple and very common in astronomy. It's just that we want to locate some dim, far away source like an exoplanet, but it happens that that source is obscured by a much brighter nearby object, like the star that the exoplanet is orbiting, right? So this is very, very common. And the hardness of this problem, to just simplify it to a bit of a toy setting, can be captured by a hypothesis testing setting instead of the full imaging setting, where we can just ask whether some dim source lies to the right or to the left of the bright star. And so the point is that the work that's cited here actually gives a quantum algorithm which is supposed to, in the idealized noiseless setting, improve on any classical telescope that solves this task. And the work does so by essentially capturing individual photons that come from the star or from the exoplanet, storing it in a quantum memory, and then performing a joint measurement on multiple photons that come in over time. So we numerically implement this specific algorithm under a standard NBQP type noise model. So in the raw setting, we just simulate their quantum algorithm from this work, but without uploading. And there's noise at the interface between the processor and the photon. In our numerics, we actually just optimize the circuit depth as much as possible. So we do something that's more optimal than any experiment anyone could ever hope to run. And then we compute the success probability of telling whether this dim source lies to the right or the left. And then what we also simulate is their algorithm optimized in no way at all, except you use uploading every time you capture a photon. And so what we see at actual noise rates that people would expect to implement, these would be the noise rates that you'd expect if you were to actually try to implement this, say, with a neutral atom quantum computer, something like 10 to the minus 3 to 10 to the minus 4 logical error, physical error rate. We see that the success probability of the raw algorithm basically just degrades exponentially, whereas uploading just works. And so our takeaway is that uploading enables a robust and practical interface between future fault-tolerant quantum devices and nature in a way that can recover the utility of many quantum learning algorithms that otherwise appear to be destroyed by noise. Great. So the last section was going to be a little bit more of a technical dive, just to explain some of the new technical results that were developed in these works. But I think for the sake of time, I'd rather answer some questions. So I'll skip that and just go to the recap of the talk before taking some questions. So I'll just move through this. And feel free to ask me about the technical aspects, like how do you actually prove that something is unlearnable unless you have exponentially many samples? I'm happy to comment on that. But that's what these slides were about. Great. Okay. So in this talk, we first envisioned the roads to usable quantum learning advantages. We saw that noise is a major obstruction, which we formalized by the model NBQP and new information-theoretic lower bound techniques, which I skipped. And with appropriate structure, even in the presence of noise, exponential speedups do remain possible. We saw that efficient fault-tolerant gadgets can create robust interfaces between a quantum computer and nature, and that this can restore some of the exponential quantum speedups that noise appears to erase. Now, looking to the future, I want to emphasize one takeaway. Quantum learning theory is a young field, and so while its high-level philosophy is extremely interesting, one for the future of scientific experiments, Thus far, quantum learning theory has lived in an idealized regime, focused on mathematical existence results rather than practically useful ones. And we've just started to lay out how we can actually start to build that road. So this leaves us with a big question for quantum learning. Can we actually realize a noise-robust, exponential speedups for practical experimental tasks with near-term quantum information processing? And when I say practical now, I mean examples that truly interface with the reality of experiments, including dealing with quantum sensors, control imperfections, and solving tasks that are actually relevant to experimental science. So in light of that question, I'm excited to share a teaser of upcoming work in which we will provide what I would classify as the first such result. So surprisingly, we show in this work that with only a single qubit, we rigorously prove that for the task of learning classical signals, such as the ones you might encounter in radar or spectroscopy, using a single ancilla qubit to implement rudimentary quantum processing can enable an exponential speedup. And we actually also collaborate with a team of experimentalists to demonstrate that this actually happens. And so we saw, essentially what we do with the experimental group is we solve a certain sensing task, which we use only exposures to a signal that last tenths of a second. And then we rigorously show that if you didn't have the ability to perform quantum information processing with just that one qubit, you'd require years of continuous sensing to learn the same property. And so that is the teaser, that is kind of the natural next progression for the field of quantum learning theory. That is a takeaway that I think comes out of the work that I've discussed today. So with that, I will conclude, and I'm happy to take any questions.
Right. Thank you very much for this wonderful talk. Yeah, so I guess we have like 10 minutes, so we have plenty of time for some comments and questions. So yeah, please, anyone, feel free to ask them now.
Yeah, I have a kind of broad question. Thank you for the nice talk. So a little while back, with my collaborators Daniel Gree and Luke Schaefer, we wrote this paper called Principal Eigenstate Classical Shadows.
Mm-hmm.
And it was kind of a very related setting. So what we were looking at was, you imagine like getting some quantum information from a sensor, and because it's like real world, it's a noisy state. So it's got some like, and we imagine that like, the principal eigenstate of this noisy state is actually the thing you want to learn.
Right. I've actually read your work. Yeah.
Okay. Cool.
Yeah.
So I guess like in that, one of the things we really kind of struggled with there, and I think it looks like you guys have spent a lot of time thinking about this, and you're actually much closer to the physics of like the kind of stuff you get from a sensor. So I'd really like to get a better understanding of like, some examples where you might actually apply this kind of learning, where you're actually getting like quantum information from a sensor. I'd like to kind of know some nice examples that you're thinking about, like quantum telescopes or whatever.
Yeah.
And also like, maybe comment on the role of like noise and principal eigenstates here. Like if that wasn't super clear to me from your talk.
Yeah. So I'll start with the first part of it, which is actually useful examples of quantum learning theory that I envision in the future. So I mentioned astronomy. One example that I have been sort of distantly involved with, but up to date with, is indeed a new example in astronomy. And the question is really, can quantum information processing help us remove noise from astronomical observations in a way that you can't do with classical post-processing? So one example, similar setting to the one I described, you can imagine capturing photons from a distant source, but it has to come through the atmosphere, right? And the atmosphere applies some kind of phase screen type noise to the incoming light, and that noise is correlated over time. It's complicated, but it has some underlying structure. And the question is, can you actually remove that noise by leveraging that underlying structure? And so that's one example I have in mind, and the answer, in fact, is yes. And you can use something similar like a swap test. Outside of the astronomy application, something I've been extremely excited about is the question of what can you do if you only have what can you do if you only have access to some small part of a quantum system? So if I'm doing, for example, sensing with nitrogen vacancy centers, which are very popular nowadays, especially at Harvard, I might imagine having some large quantum material or molecule which lies above the surface of this diamond that has nitrogen vacancy centers within it, and the nitrogen atoms are extremely sensitive to the magnetic fields that come from whatever system is outside. And the point is, quantum learning theory treats it as if I could just measure every single atom in this molecule, which is obviously experimentally intractable. And in practice, what I really have is one or a few probes that get some incomplete description of the system. And a question I might ask is, what is the extent to which I can learn like a really complete description of the system? And so recent work that the Kotler group has been developing actually shows that, extremely surprisingly, that very generically, if you even only had like order 1 number of probes coupled into a very large quantum system, you can actually reconstruct the entire Hamiltonian of the system efficiently. And building out applications of this is something I'm extremely excited about. And then third, of course, I just touched on classical sensing. So instead of learning about quantum data, can you use quantum processing to learn about the classical world? And that's something I've been working on. Now, to touch on the principal eigenstate stuff, actually, the example I showed, suppose I want to measure like trace of O rho cubed. Actually, that's mathematically equivalent to asking about learning. I mean, it's equivalent to learning the principal eigenstate of a rank 3 density matrix, right? So the question of, it turns out that swap tests and quantum principal component analysis and the work that you did are all intimately tied together by the same quantum circuit. There's a generalization of a quantum circuit which kind of encapsulates all of these examples. And the point is, as long as you have as long as you know that the additional, rank 2, rank 3 contributions to the principal eigenstate you want to learn have sufficient structure as you laid out, you can, quite generically deal with the noise. But when the noise now occurs, like suppose you have some rank 3 state, but now the quality of the interface between your quantum data and your quantum computer is quite poor. You might imagine having a local, like the most apt noise description is a local noise model that acts on every site of this quantum system. And suddenly that amplifies the hardness of your problem from, orthogonal rank 3 noise to highly overlapping high rank noise. And so it basically becomes the case that when you consider a noise model like NBQP, the advantages that you have from stuff like virtual distillation, quantum PCA, these things tend to disappear.
Okay. And sorry, I'll just ask one quick follow-up to that. Do you think, like, say, looking at this example of photons through the atmosphere or any of the others you've looked at, is that type of noise likely to preserve ensure that the principal eigenstate is actually the state you're trying to learn?
Right, so that's the point. The reason that in the atmospheric setting, it does preserve it because generally the atmosphere, so this one example, which is, to be honest, like kind of offhand, it's not something that I think applies more generally to other quantum learning problems, but in this one specific setting, it happens that the atmosphere acts as a unitary noise. And so because of this, and the fact that the unitaries are correlated over time, because the atmosphere like drifts, it physically drifts at some rate, you actually gain the ability to decode the noise that was in the state. However, of course, if it was some kind of Markovian dissipative noise, then you'd lose the ability to do that, and the principal eigenstate, for instance, would just be completely wiped out.
Oh, so my question was whether the principal eigenstate is the same as the original state.
Yeah, it's not. If you have dissipative noise and Markovian noise, it won't be. But if you have unitary noise, you can you can do post-processing and then basically obtain the initial state back up to some small corrections.
Okay, cool. Thank you very much.
I think, yeah, we have time for one more quick question or comment from others. Okay, maybe I can just ask one quick question for me. So like maybe like a more general one. So like you've shown that like when you have this noise that you lose this advantage, but you were talking specifically about the certain kinds of circuits that's like enabling these advantages for learning tasks. But is it like, are there learning tasks where like it doesn't, like the noise doesn't hurt you? That's no.
So it's not known. Well, it's not publicly known. We have. It's basically the point is that. So okay, let me maybe be a little bit more precise. In the paper, Noisy Quantum Learning Theory, we gave an example, which is a very, very toy example, in which you might imagine that, you want to do purity testing, so you want to run the swap test, but it happens that your state already has some built-in error correction properties. So in that case, you don't actually hit the worst case no-go because you can use those error correction properties to run the swap test noise robustly. But that's not quite the question you were asking, I guess. The question is maybe more generally, is there some family of learning problems where you might not have a priori error correcting structure, but there's still a robust quantum advantage? And to that, the answer is there does not exist a known one, but some work that we have upcoming probably in the next few months will show that in the setting where you're doing optical sensing, so you might be doing radar or just sensing with an optical cavity, it becomes possible if you assume if you gain the ability to do certain quantum information processing to actually prepare your sensor in a way that it retains an exponential speed up in the presence of noise.
I see. I guess we'll just have to look forward to that one.
But yes, so your question, it has not been known there is no known example thus far, mainly because quantum learning theory has essentially only relied on the swap test and Bell sampling.
Right.